I'm going to put some side note here on top before we get into this elastic collisions. Right? There are basically three types of collisions that we should be aware of. Right? First one is like elastic collision. Okay. Oh yes, right. Yeah, I should share this. I think that would be nice if I share that. Sorry. Can you see? No. All right. So there are elastic collision. Okay. And the second one is inelastic collision. And the third one is completely inelastic collisions. So these three different types of collisions are going to be talked about today. Okay. Um, and they all have characteristics. Okay, that can be identified. Most collisions are inelastic collision. Okay. In human scale at least. Okay. Elastic collisions happen at very like subatomic levels, and if you have like two molecules like coming together, crashing in together, or two atoms coming crashing in together, and because it is surrounded by electrons, they don't even touch, and then just bounce off. You know, certain other collisions like billiard balls, right, or marbles, they behave as elastic collision. Okay, but it's not perfectly elastic. Inelastic collisions pretty much happens all the time, okay, in human scale. Completely inelastic collisions happen when things stick together after they collide, okay? So, like for example, when bullet penetrates into the block of wood and gets embedded inside, right? And they block a wood and the bullet becomes like one mass, that's completely inelastic collision. Like we did those kind of problems already, but we never identified it. Anything that collides and bounces off, like baseball being hit by a bat or tennis ball, right, hitting a wall and bouncing back out, or like tennis racket hitting a tennis ball, or golf ball being hit by a golf club, they're all inelastic collisions. Billiard balls, those pool, like when you play pool, right? They behave as elastic collisions, believe it or not. Okay, even though they may not be perfectly elastic, but they behave as pretty close to as elastic collision as possible. So we'll show some more examples of this. But for now, we're going to try to explain about this elastic collision, John. All right. Now, for elastic collision, there are certain characteristics that we can be um, talking about. First of all, when collisions happen, it has to be a closed system, right? That means there's no mass introduced into the system or there's no mass lost in the system, right? So closed system means all the mass is conserved, right? There's nothing lost or gained. An isolated system means there are no external forces acting on the system during the collision. Okay, so all the collisions so far we're going to talk about is closed system and isolated system. So just make sure you understand that these two conditions have to be met. So the linear momentum P is always conserved in all collisions, right? So all these collisions, right, the linear momentum is conserved. And the linear momentum is conserved because it is an isolated system. Because remember, sum of all forces is equal to delta P over delta T. If this external force, if this goes to zero, then this must go to zero. There's no negotiation. That's why when there's no external force happening, then the linear momentum has to be conserved, which means the change in linear momentum has to be zero. There's no change at all. Okay? So always conserved in closed and isolated system. Okay? Whether or not collision is elastic or inelastic, right? It doesn't matter. Because all forces are all internal forces acting in there. Internal forces cancel out because they act on the same object or the system within. Now, here's another thing. This is the only thing that is important for elastic collision. If the kinetic energy of the system is also conserved, so if I have kinetic energy before the collision of the system, and after the collision, I look for the kinetic energy and I calculate it, and they happen to be exactly the same, only then the collision is known as elastic collision. So if and only if kinetic energy is conserved, then collision is elastic. So this is very, very important. So to find the kinetic energy, you have to find the kinetic energy of everything within that system. When you have two objects moving, find the kinetic energy of both objects. And after the collision, you have two things moving, find the kinetic energy of both objects. Compare it. If they are equal before and after the collision, then it is elastic. If they're not equal, then it is not elastic. So therefore, elastic collisions conserve energy and momentum. Okay? To be more precise, kinetic energy and momentum. Okay? So, what happens? I have mass 1 moving and colliding with mass 2 that is at rest. This is the initial condition. Then after the collision, I have mass 2 moving and mass 1 is also moving. In this case, we have to have mass 1 and mass 2 and mass 1 and mass 2 before the collision and after the collision. They both have kinetic energies. Well, this one doesn't, right? This one only has kinetic energy for the mass 1, but after the collision, both of these have kinetic energies. So when I find the kinetic energy of this and compare it with the kinetic energy of this and this added together, and if they are equal, then and only then this collision is elastic. Okay? So first, this has to be true. The initial total momentum must equal to the final total momentum. And these two have to also equal to each other. So we already know, so since these are only in the x direction, so we say m1 v1 initial in the x must equal to m1 v1 final plus m2 v2 final. So this is true only for this scenario. Okay. And similarly for the kinetic energy of mass 1, which is 1 half m1 v1 initial squared, must equal to the kinetic energy of 1 half m1 v1 final squared plus 1 half m2 v2 final squared. So when I add these two up and compare it with the initial kinetic energy, they better be the same. Okay? So we will put more examples later in this. So let's take a look at a scenario where I have two-dimensional collision. So here, if I have two identical masses that are spherical, think about like a billiard ball, right, or pool balls, right? Equal mass, and it comes in with the initial momentum of mass 1 coming in, colliding with mass 2, which is same mass as mass 1, at rest. Okay? So two particles of each mass have elastic collision, and a target particle being initially at rest. So this is the target ball, and this is the incident ball. Incident ball is the one that's coming in, that's moving, and target ball is what the incident ball is crashing into. Okay? Show that unless the collision is head-on, the two particles will always move off perpendicular to each other after the collision. So if it's a head-on collision, what's going to happen if these two are same masses? This, when it crashes into this, will stop, and this will take over and move on. That will happen. Okay? But if they hit slightly off center, and then after they collide, they have to move at a right angles off of each other. And how can we prove that? Well, we know that sum of all momentum initial must equal to sum of all momentum final. Okay? We also know sum of all kinetic energy initial must equal to, right, sum of all kinetic energy final. Well, in this one, we have to break this up into x and y components of each other. So this is going to get a little complicated, okay? But if we were to look at the kinetic energies, the conservation of kinetic energies, these don't require any direction at all because there are energies and these are scalar quantities. So initially, so this is the initial condition right here, and this is the final condition. I only have this mass, one of the masses, right? So 1/2 m times v1 initial squared is my kinetic energy. Okay? Then the final kinetic energy for both of these is equal to 1/2 m times v1 final squared, right? Plus 1/2 times same mass, right? Identical balls, times v2 final squared. Now, if you take a look at this, I have 1/2 m, 1/2 m, 1/2 m. If I divide both sides by 1/2 m's, they will all cancel out to 1. So this v1 initial squared is equal to v1 final squared plus v2 final squared. Now these are basically the magnitudes of this and magnitude of this. So this initial v squared must equal to this final v1 squared plus final v2 squared. This only happens if this looks like a Pythagorean theorem, where this looks like the hypotenuse square is equal to adjacent squared plus the opposite squared, right? So this can only hold true if this is a right triangle. So this angle here, when they go off, has to be perpendicular to one another. It has to be the right angle. Now, of course, like if you play pool, you don't always hit the cue ball right at the center all the time, right? Like you have, like sometimes if you want to, like, follow the target ball, you give a top spin, you hit the top of the cue ball, right? If you want to have a like backspin after you hit it, you hit the bottom of the cue ball, right? So you have a backspin. And then if you want to like little English to the left, you know, after you hit the thing, you hit the like, top of like left, and it will like spin out. So all those spins don't count here. We're just talking about hitting dead center all the time. Right? This only happens if you hit just dead center. So the cue ball, like if you have a cue ball here, you're hitting exactly at the center with the cue stick. Okay, because this, if you hit it here, you'll like backspin it. Hit it here, you'll roll it forward. Hit it here, you got English, top and left English. So hit it here, it spin out like sort of sideways after hit it. So we're not talking about that. Okay, so this proves that this is Pythagorean theorem, right? So this is right. Therefore, this only works if the triangle is right triangle. Therefore, the angle oops, must be 90 degrees. Okay, so it's a little trick to know. Okay. All right. All right. Now let's take a look at an example problem with some numbers in it to see if it is a elastic collision or not. Okay. So here's an example problem. We have two-dimensional collision problem. Is it elastic or is it inelastic? We don't know. Right? You're only told that it makes an elastic collision. But we have to fact check this scientifically. We don't know if it's true or not. We're just told that. Okay? So, okay? Because we don't know if this is true. But what we do know is that we have a 5 kilogram object that comes in at 6 meters per second along the positive x-axis, collides into this 2 kilogram mass that's at rest. So it comes in, it collides. Then once it collides, my 2 kilogram mass goes off at 5 meters per second at 30 degrees to the horizontal, right, or 30 degrees to the positive x-axis. Right? And this 5 kilogram, which is the incident ball, goes off at a certain angle that we don't know. Okay, so here I'm going to make the 5 kilogram ball a purple ball so you could see it better. And I'm going to make this 2 kilogram ball aquamarine blue color. Okay. I don't want to call it a blue ball. So here, if you actually take a look at this, we know that this 5 meters per second at 30 degrees is going to have components of x and y later. And so is this. This is going to also have x and y components. So you have to break them up. Okay? So let's think about what's happening. I'm going to divide this thing up into two parts. One's going to be the x-axis, and the other one's going to be y-axis. Okay? So let's take a look at x. Let's take a look at y. So we're not going to assume either elastic or inelastic. We're not going to assume anything. We're just going to assume to be maybe inelastic first. Okay? And we're going to prove that if it's elastic or inelastic later, once we get the kinetic energies. So here, we have, in the x direction, we have, right, sum of all momentum in the x direction must equal to sum of all momentum final in the x direction. Okay? So initially, right, I could have, right, momentum initial of incident in the x direction plus the momentum of initial of target in the x direction. Okay? That has to equal to, right, the momentum final of incident in the x direction plus momentum final of target in the x direction. That's the momentum right here, right, for the target, and that's the momentum for the incident final. Here, this is just M, so you could say this is M incident, and this is M target, okay? So M incident times V initial incident, right, in the X is what this momentum in initial incident X is. That's what this is. Plus, right, mass target times V initial target in X direction. Well, we know this is 0, you know. V initial target in the X direction is 0. And this is the V initial incident X. This is what that is. That has to equal to, right, mass incident times V final incident X plus mass target times V final target X. Now we know that this is 0. Mass incident happens to be 5 kilograms, so we could put 5 kilograms in there. Then initial velocity for the incident in the x direction is 6 meters per second. Are we okay with that? Yeah. Plus, this is 2 kilograms times 0. that is equal to. Here, this is my V, this is my V final, right, of target X, and this is my V final of target Y. Similarly, this is my V final incident X, and this is my V final incident Y. Now this is the angle theta. Okay, this is the angle theta. This angle is 30 degrees. We already know that. So for this one, we know that this has to be 5, right, times sine of 30 degrees. Does that make sense? Right? Because this is 5. So 5. So if you want, you could say V final target sine of theta. You could put that in there. And that sine of 30 is just half. So it's like 2.5 meters per second y hat, right? For the x, that is same as V final target cosine of theta, which is 5 times cosine of 30, right? What's cosine of 30? 0.866, and 5 times that, right? So what's that? It's like 4.33. Let me check. Right, so, oh my God, I have no more batteries. For that plate. Oh, somebody stole my batteries. Yeah. All right, this is no good. Somebody do the calculation. No batteries. That's it. Well, anyway, let's move on. It's okay. We're going to have to eventually get some calculator. You have a calculator? Yeah? Yeah. Can you do 5 cosine 30? I got 4.33. So I was right? Oh, wow. Okay. So 4.33 meters per second x hat. And these, we don't know because I don't have any value for this. All I know is that this here is V final incident. And this is angle theta. And this is basically same as V final incident times sine of theta. But don't forget, this theta is in the negative direction. So we really don't know, right, what the negative is here. We're going to eventually get that, though. And this is also V final incident times cosine of theta. But that's all we know. We don't know any numerical values for those. So for this side here, we say mass incident is still 5. V final incident x is just V final incident times cosine of theta. That's all we know. Right? Plus the mass target, which is 2 kilograms, times V final target X, which is 4.33. So Now we can have here, this is 30 plus 0, which is just 0, right, is equal to, 30 is equal to 5 VF incident cosine of 30 plus 8.66. So let's bring this to the other side, and what do we get? We get like 21.34 something. Is that what it is? 21.34 is equal to 5 VFI cosine theta. Right? So my VFI incident is equal to, right, 21.34 over 5 cosine theta. I have two unknowns here. I don't know VF1 and I don't know theta. Did you check my math? Am I okay? Yeah. Okay. So this is I only have that. All right. Now we're going to need a second equation that's going to have some of these two variables. So let's take a look at the y direction now. So sum of all momentum initial in y must equal to sum of all momentum final in y. So initially, I have momentum initial incident y plus momentum initial target y must equal to, right? Must equal to. Here I have momentum final incident y plus momentum final target y. Okay. Well, initially for the incident ball, how much is it going in the y direction? Is it going in the y direction at all? No. 0. How much is my target ball going in the y direction? Ever? 0. So this is also 0. Right? So this whole one side is 0. So 0 is equal to, here I have m times m incident times v final incident y, right, plus m target times v final target y. So my 0 is equal to now, right? Maybe I should make this blue. So 0 is equal to mass incident, which is 5 times VFIY is VF, right, I times sine of theta plus the mass target is 2 kilograms times VFTY. VFTY is 2.5. So if I multiply this, this becomes 5, right? So here I got 0 is equal to 5 times, right, VFI sine theta
plus 5. So if I bring this 5, I get negative 5 is equal to, right, 5 VFI sine theta. Divide both sides by 5, and I get negative 1 is equal to VFI sine theta. This looks familiar. If I substitute this VFI here that we calculated into here, so if I put that in there, what do I get? I get negative 1 is equal to now, right, 21.34 over 5 times cosine theta times sine theta. Isn't that same thing? Sine over cosine is tan theta. What's 21.34 divided by 5? Is that 4 point something? Is that 4.2? What is it? 4.265? What is that? 21.34 divided by 5. All right, 4.26, what is it? 8. All right, times tan theta. So my theta now is equal to, right, tan inverse of negative 1 over 4.268. So what's my angle? I wish I had a working calculator. What you got? Negative 13.187 degrees. So that's the angle, and that makes perfect sense because this is below the x-axis, so this better come out to be negative angle. And we got negative angle right here, negative 13.187. Booyah! Right? So we plug this back into either here or here. It doesn't matter. Right? Let's plug it in here. Let's plug it in here. So what happens if I plug in negative 13.187, or plug it in here? So VFI is equal to 21.34 over 5 times cosine of negative 13.187 degrees. What is that? What you got? 4.38 meters per second. Boom. So I got both answers. Now comes the magic. Now comes the magic. Is it elastic collision? Well, to find out if it's elastic collision or not, we have to find the kinetic energy before the collision and kinetic energy after the collision. So finding the kinetic energy initial, the sum of all kinetic energy initial is equal to, is just kinetic energy of incident ball initial, right, plus the kinetic energy of the target ball initial. Well, initially, I have 1/2 mass of incident times V initial incident squared is my kinetic energy initial, plus plus initial kinetic energy of target is 0 because it wasn't moving. This was not moving. So kinetic energy is 0 for the initial. So if we plug these values in, let's find the kinetic energy. Right? So 1/2 times mass incident is 5 kilograms times initial velocity incident is 6 squared. So what does that come out to? Like around 90? Yeah, 90? 90 joules. So the total initial kinetic energy comes out to 90 joules. Right? Now what? Now what? Let's find the kinetic energy final. Sum of all kinetic energy final is equal to kinetic energy of the incident ball final plus the kinetic energy of target ball final. So that is equal to 1/2 m target v final target squared plus 1/2 m, I'm sorry, that's not target, that's incident, mass target times v final target squared. Therefore, if you plug in these values, I have 1/2 times 5 times V final target, V final incident is 4.384, right? So 4.384 quantity squared plus 1/2 times 2 times VF target, which is 5 meters per second. So this is VF target, right? So that's just 5 squared. So if you work this out, you're going to get, well, this is going to come out to 25, right? So this is plus 25 here. What is this? This is like a little more than 16 times 2.5. So what is that about? 30s? I got 48 point what? 49? 049. Add them up. What do you get? 73.049? Right? So 73.049 joules. So, is my kinetic energy conserved? So my sum of all kinetic energy initial does not equal to my sum of all kinetic energy final. Matter of fact, I lost some kinetic energy because I started with 90 joules. Now I only have 73.049 joules. So I lost some kinetic energy. Therefore, they're not equal to each other. So what kind of, is it elastic collision? And the answer is no, right? Therefore, right, it is inelastic collision. So you were lied to. Okay? So it is inelastic collision. So this is BS. All right? Wow, that was a lot of work, huh? That was a lot of work. So, yeah, you have to sometimes prove it to see if it's elastic or not, or inelastic. All right? All right.
I'll just leave it up here for a little bit so you can absorb. Okay. Any questions? All right. All right. So this was a good problem. This was a good problem. All right. Yeah. While you're working on this or copying that down, we're gonna have to do the other thing first before I show that demo. So let's take a look at an instance. Okay. Let's say I have an elastic collision where target ball is at rest. So this is the target ball again. And this is the incident ball. So mass 1, mass 2, or mass incident, mass target, just to make it more distinguishable. I made it different colors. And if it is elastic collision, two conditions must hold. One is the total momentum initial must equal to total momentum final, and total kinetic energy initial must equal to total kinetic energy final. So these two must hold true if it's elastic collision. So if I were to take a look at what we did earlier, but this time it's actually easier because it is one dimension. It's not two dimensions. So initial momentum is just the mass of incident times velocity incident initial. It's just this. That has to equal to, right, mass 1 V1 final plus mass 2 V2 final after the collision. So this is after the collision. So this has to be true. Now, if I bring this to the other side, what I have is I have M1 V1 initial, and then this one is minus M1 V1 final is equal to, right, M2 V2 final. What I did was now I factored out the M1. So I only have this. Is that okay? Now that I'm going to square, well, I'm going to divide both sides by M2. Okay? So I'm going to divide both sides by M2, M2. Then I have basically this goes to 1. So I have V2 final on this side. And I have M1 over M2 times this. Now I will square both sides. And this is what I get. Okay? This is what I get. Now let's take a look at the energy part. Here, I have the initial kinetic energy. It's just this M1 moving. So I only have kinetic energy of M1 is equal to kinetic energy of M1 final
plus the kinetic energy of M2 final. Okay? Are we okay with that? Now, take a look. I will cancel out my 1/2. And I'm going to bring this to the other side, just like I did with this, right? So M1 V1 initial squared minus M1 V1 final squared must equal to M2 V2 final. Then I factored out the M1. Right? I factored out the M1. And if I divide both sides by M2 again, this is what I have. This becomes 1. So my V2 final squared is equal to this. But this is difference of perfect squares. You can factor it out to that. You know that, right? That's from Algebra 1, right? So notice that these two are exactly the same. So I can set these two equal to each other. And let's take a look at what happens then. Okay? So if I set these two equal to each other, I have on this side, I have M1 over M1 squared over M2 squared. I'm going to just go with one color now. V1 initial minus V1 final squared. So I'm going to do that again. V1 initial minus V1 final must equal to. I'm going to do this side now. I have M1 over M2 times V1 initial plus V1 final times V1 initial minus V1 final on this side. Look at this. I can cancel these out, right? And I can cancel one of these out. So, if I distribute this through, right? If I distribute this through, or if I multiply this to the other side, and let's solve for V1 final. Okay, let's solve for V1 final. So here I have M1 times V1 initial minus V1 final is equal to. Here I'm going to multiply the V2 on this side. M2 times V1 initial plus V1 final. Distribute this through. M1 V1 initial minus M1 V1 final is equal to M2 V1 initial plus M2 V1 final. I want to bring this to the other side and isolate the V1 final and bring this here. So I get M1 V1 initial minus M2 V1 initial. So I brought this over here. I'm going to bring this to the other side and it becomes positive, right? So I have M1 V1 final plus M2 V2, no, V1 final. Now what? Now what? Factor out the V1 final. And I get M1 plus M2. Here, if I factor out the V1 initial, I get M1 minus M2. If I solve for V1 final, my V1 final is now equal to V1 initial times M1 minus M2 whole thing over M1 plus M2. Holy shnikes.
Now, let's take a look at what happens. What happens when I look at this equation? What if my M1 and M2 are equal to each other? What if they're identical? What would my V1 final be if M1 is equal to M2? By looking at this. Zach? It'll be 0, correct. Because this would be M minus M, would be 0. So 0 over anything doesn't matter, and 0 times anything doesn't matter. So if
M1 is equal to M2, then V1 final is equal to 0.
Outstanding.
What about if M1 is greater than M2? Then what?
What's my V1 final? Is it positive or negative or 0? If M1 is bigger than M2. Positive.
Then my V1 final is equal to positive. That means it's going to
Continue to go in the positive direction after the collision.
What if M1 is less than M2? Then what?
Negative. That means it's going to bounce backwards. So let's see if that's true. Right? This is science class, so we have to prove it. Right? Let's see if that's true. So here, Justin, are you taller than me? I'm like 6'4", so.
I think I'm 6'5", so I think I'd be
Wow.
about there.
All right. You're about the same size. Can you get that tube down?
Yeah.
Yeah. All right. He's like this much, so he must be like 6'5". All right. Cool.
Have you been before?
Yeah,
My part of the experiment now.
Yeah, you're gonna have to be part of the experiment. So I'm gonna control the camera so people at home can actually see what we're doing here, right? Now I had this track that I could actually place this. Well, see. Now I'm gonna actually have these cart. We're gonna have this cart, and these carts are like very, very, very. It's a very smooth wheel. Right? Just put it this way, not perfectly level. And they're identical mass. Right? So let me see if I can bring this camera to the other side so people at home can see what we're doing.